we go.
Just let me tell that it's a great pleasure to have the first talk of Nikita, who's going to speak about exciting connection between quadratic forms and string theory.
Well, thank you for possibility to speak here. Well, today it's not in between of quadratic forms and string theory, but that's about the connection of these lattice summations and certain functions from string theory. So these functions are called modular graph functions. Let me recall the main object of our study. So what do we have? So here we have a certain summation as here, and we sum over the set of vectors, the pairs of vectors x, y, such that they belong to the first quadrant. They're like lattice vectors from the first quadrant, and in each pair the determinant is 1. So in a sense, we are like summing over the set of lattice parallelograms of area 1. And so here we take the length of sides square times the length of diagonal square. And we prove this theorem like in several ways, and I know at least 3 proofs, quite different for this statement. And today the goal is to connect it to so-called modular graph functions. And I will not speak like much, with proofs about that. I just explain what is that actually. Okay, so just formula, in general formula is as follows. So here we have as function c. Here we have gamma, it's a graph. Okay, and tau is a point from the upper half plane. Okay, so tau belongs to H, which is just, this complex numbers with imaginary part bigger than 0. Okay, so what we have on the right? So on the right, we have a quite complicated expression. Like later, I will explain it in more details. For now, maybe let's look here. So tau is a complex number, and its imaginary part is denoted by y. Okay, and so this y can be seen here. So here you divide by pi, and then you take a product of some expressions. And what are the expressions here in the denominator? That's complex numbers p alpha. So alpha ranges from 1 to a certain number w, and actually it's number of edges of the graph. So w is the number of edges of the graph. So for every edge of the graph, you have some variable. Okay, and so these variables, they belong to lambda. And lambda, that's just lattice generated by tau. Okay. And so you see lattices, you see certain products, and so far we cannot say much about this product of delta functions, but well, it will be on the next page. So that's the main object in this modular graph functions topic. Okay, now let me explain what is that. Okay, so here I can just quote what they say because I could not say that I understand, all these things very well. So here we have superstring amplitudes, whatever it means, and they have genus 1. This I explain what it means. And they are type 2, and then you expand it by the parameters, and then you are looking for the coefficients there, and you try to understand how they look like. And actually, that's exactly this modular functions. So when you look for this like low energy expansion of genus 1 type 2 superstring amplitudes, so there you see numbers, and these numbers are, well, say functions. These are these associated modular functions. And the graphs are Feynman graphs. So if you know how to use Feynman graphs, how they appear, when you compute the amplitude, these are the same Feynman graphs. And well, that's all happen on a torus, so in genus 1. And so in this talk, the first part of it, which is dedicated to modular functions, modular graph function, it follows the following articles. So first of all, there is a note of Don Zagier. It's called Notes and Lattice Sums. And several articles cite this unpublished work. So you can find this work in Google Scholar. So it has like 8 citations, but it's not possible to find a PDF. I have in possession another PDF. It's also unpublished article by Don Zagier, and my PDF is called Evaluation of Lattice Sums. It's dated of 2009. And it seems that exactly this thing. So just maybe different people call it by different names, so maybe there were different versions. Anyway, so I think it's all started from there. And then there's an article of Hocker, Green, and Van Hove of 2015. And this article is very popular. So it has like maybe 200 citations. And that's exactly about this modular structure of the genus 1 type 2 superstrings, low energy expansion. And it's quite long. You see, it's 70 pages, and a lot of stuff is proven there. And actually, I didn't know about that article. So I asked several people about these formulas. I proved certain results. And then maybe like only 3 weeks ago, I found this article. And actually, many things that I proved are already proven there. So 10 years ago, ahead of me. And so in this article, there are a lot of results, but also there are some conjectures, and these conjectures are proven. For example, in the next article, or also I will tell you something about these conjectures and their proofs. And here you see that from the Journal of Number Theory. So actually, these people, they started in string theory, but like eventually they're just nice formulas, number theoretic formulas. You can prove them and expand them. And I think it's more number theory than physics. And also today I will talk about like last mile results on telescoping. Telescoping. Actually, it's difficult to understand what is proven and what is not proven in all these articles in string theory because there are hundreds of them and a lot of formulas, sometimes different notations. So actually, maybe everything that I'm going to prove is already proven somewhere there. Okay, so that's the plan for today. Now let's go to the string theory and Feynman graphs. So I explain what I understand. So how Feynman graphs appear is that we have a certain model for particles and how they interact. And every edge means a particle propagation. And it may be some internal or external particle, some particles collide, or it may be some internal particle. So whatever it means, virtual. And the vertex corresponds to interaction. So for example, two particles, they merge, they collide, and then you have just one particle. And then there is a thing which is called a loop, and that's called a quantum fluctuation. Again, so when you speak about, let's say, quantum string theory and like some quantum interactions, you have loops. Why it's called a quantum fluctuation, I have no idea. But anyway, that's what people say. And you have internal edges and external edges, and the external edges are actual incoming and outgoing particles. And then what people do, people assign variables to the edges. So for every edge, you have a variable, and so on. And then you multiply them, you integrate them, and so on. So that's how it's all things work. So basically, you can just look for say that it's just definition. You have a graph, and you have variables assigned to every vertex or to every edge, and then it may belong to some space. You multiply them, you integrate over them, and then you ask what is the value of the integral, what is the property of the integrals. Okay, that's kind of my short introduction to string theory. Okay, now let's see how we can associate certain mathematical objects to these graphs. Yeah, and also, as I told you, so usually these graphs, they appear when you try to look for the like expansion of certain divergent integral. you integrate something over all the paths, and then like naturally you have some graphs, and kind of the terms of your expansion, they are encoded by graphs. Okay, now how to define these modular graph functions. So first of all, there is a loop one. So one loop function. And that will be the Eisenstein series. So let me explain what it means. So here we have a graph. So here we will have graphs without external edges. So again, rather different notations. I will draw here the graphs without external edges. So for example, if you have just one loop like that, it means that here you have a variable p alpha. It belongs to the lattice. And lattice, as you remember, it's z tau plus z. Then it's kind of outgoing from here and incoming from here. And actually here there are no additional conditions. So all the conditions are satisfied. And so here you just need to take a sum. So for example, to this picture, they correspond to the sum over 1 over n tau plus m. And here you sum over all n m, which are integers. Okay. Well, even though it's divergent. So then you should add something. You should say, okay, so I should omit an m which is 0. So usually people just write some prime, just all no not infinite terms. Again, it's divergent, but okay, you can define it. There was a question.
You answered it. It was just a comment that you couldn't divide by zero.
Well, yeah, first of all, you cannot divide by 0. Second, even if you just remove 0, still it diverges, but it's a formula. So maybe if maybe sometimes when you work as a string theorist, you don't care about convergence. Well, anyway, so that's just how to define it. Now, how to get something convergent. So let's have again a loop, but with several points on it. Okay, so here you have several vertices. Now you have a variable corresponding to every edge. I don't know, p epsilon. Now let's look at on the condition. So let me just show the condition. So here we have certain product of delta functions. So what is the product of delta functions? So actually here the condition is follows. So if you take a vertex and you look at the labels of the incoming edges, the sum of labels must be 0. So what it tells here. So here you see, so here is the product from 1 to n. So here we have n vertices, number of vertices. So for every vertex, you have such a condition. And then here I just write that, okay, so here the sum, the delta of this, so this sum must be 0. And this sum is just the sum of the labels on the incoming edges, well, with signs. So for example, if here on this picture, I have some orientation, like that, for example, right? Then it means that I should have that p alpha plus p epsilon is 0, p epsilon plus p delta is 0, p delta plus p gamma is 0. But for example, here I have p alpha minus p beta is 0, right? So I should say that, for example, if I switch the orientation of an edge, I change the sign of the label. And then what I do, then I take the product of all of them. So here I take a product of all this y divided by pi p something square. And in this case, you see they all the same up to sign. So in this case, your function will be just the sum of the y power 1, 2, 3, 4, 5, pi power 5, and here n tau plus n power 5. And again, you write here prime, which means that you don't look for the summand which is 0. so you avoid 0. But now it's a well-defined function that's called non-holomorphic Eisenstein function. It's called E5. It's non-holomorphic Eisenstein function or series. So what is good about this function? It's SL to Z invariant. SL to Z invariant. Right? So if you just act on tau by SL to Z transformation, it will be like A tau plus B, C tau plus D. Then you can see that this thing is invariant. So that's a modular function. That's why it's called modular graph function, because usually we get here modular, like SL to Z invariant functions, and they're associated to graphs. Okay, any questions so far?
Could you go back one slide? I lost how you got y to the 5.
Well, just for every term here, I should have y divided by the label square times
Okay,
pi.
that's right. Thank you. Thank you.
Okay. Um, okay, so the power of y is the number of edges. Okay, so here, and also the number of edges, that's called the weight of the function, and this low energy expansion is graded by the weight. So the graphs with smaller number of edges, they appear earlier. So they have like, first contribution. Okay, that was about one loop graphs. That's Einstein series. Now let me explain what happens with two loops. That actually is a C alpha, the C A B C. So maybe let me just erase it, everything here. Oh, good. Now, sometimes this say CABC, they draw like that. So you have just interaction of three particles. Okay, and so you have three edges. So you have P alpha, P beta, P gamma. You have one condition, the sum must be 0. So it's the sum over all like P alpha, P beta, P gamma from the lattice, such that the sum of them is 0. And here you write y power, well, pi P alpha square, well, cube, P beta square, P gamma square, P cube. Okay, that's like C111. Or sometimes people draw the same graph like that, just to say that it's called two loop graph. It's like, well, 2L, two loop. So, but it's the same, because if you orient edges somehow, the conditions for both vertices are just the same condition. So here the sum of labels is 0, and here the same sum of labels is 0. So you may say that you have just one vertex and like three like external edges. Or you may say that we have this picture. Okay, so what is that? That's a function that's S111, C111 of tau. Okay. And now let's put there tau equals I. Okay. C111 of I. Now what you have? You have sum. Here you have 1 cube, pi cube. And here you have, well, n1 I plus m1 square and 2I plus m2 square times n3I plus m3 square. Okay, and if you denote this by x, this by y, then this will be just minus x plus y, right? Because the sum of them must be 0. So actually this expression, that's exactly, well, 1 divided by p cube. sum over all 1x square y square x plus y square, where x and y are lattice vectors. Again, you put here prime, and prime means that we don't consider summands which are infinite. Because, like, for example, x may be 0, and here maybe, let's say, p alpha may be 0, but we don't take these terms. Okay, so actually the sum that I considered before the previous two lectures, that's exactly C111 of I.
Maybe disagreeing for me because your sum was over the quadrant.
Yeah, so you're right. So now let's look here. Let's look for this sum here. So here indeed, I look for the sum over the quadrant, and here also I have conditions that determinant is 1. But actually, using the standard tools of number theory, you can extend it and you can compute it. So basically, if you know the sum for the quadrant, and with determinant 1, then you know how to compute the sum for the like half plane. Then you know how to extend it to determinant 2, 3, n, and they all compute it, and they all agree with the computations of these guys. And actually, that's exactly what happens in this not published article of Sagir. So he considered exactly C111. He just said, okay, so what if I have a sum of this type? So you have a lattice, and then you just look at the product like that over all triples with some 0. And he computed it. He found that it's more or less the constant. So it does not depend on tau, actually. We will see later also what is dependence. So the dependence is not very, no. Well, we will see it later. So that's the content of the article. Yeah.
I have a question. You said that the computation of the over the quadrant implies or can be used to compute readily C111.
Yes.
I suppose the converse is also true. Knowing C111, one can readily compute the sum over the quadrant.
Well, in the by the method how I do that, yes, but in general, no, I don't think so. So this sum that I consider, they are kind of more general. So it means that here I can compute the sum for every part of this thing. So I can start with any angle and just look at the vectors inside this angle, and I know
So
this.
one could say that your method is somewhat stronger.
Yeah. So it's kind of it computes smaller parts, and then like I build out of them the bigger sum.
Okay, thank you.
Yeah. Well, it's more actually it's more elementary because how the gear did it on this article is how it was done like in the next articles. So well, you look at this function, you observe that it's modular functions, and you compute the first few coefficients. Then you estimate it grows at infinity. And then you say, well, you have some identity because you know that kind of as the usual story with modular functions. If you found the first few terms, you know the dimension of the modular function of given degree, and then you know that it must be 0. And so you prove the identity. So the proof was very not direct. And with a lot of, no, not a lot, let's say half a page of computations, but still by some argument saying that if something is modular and with small growth to infinity, with few terms, with the first terms zeros, then it must be 0. Well,
Uh-huh.
and
Yeah.
most are just elementary. Just look at some telescopic series and you see that it's true. Okay, that was C. Okay, now what is CABC? CABC just the same, but when you put here some powers, like PA power to A, PB power to B, P gamma power PC, and here you have A plus B plus C. Okay, and so that gives you CABC. And this article of this of Hocker, Green, and Van Hove, that mostly dedicated to this kind of summations, like C, A, B, C. Because you can understand almost everything about them. Because there are relations. I will show them later. But there are more complicated graphs for sure. For example, what is D4? D4 is when you have two vertices and four things here. Well, and D5 is when you have like five. Okay. And this CABCs happens when you put here A points, here you put B points, and here you put C points, C vertices. So like similarly as we did for Eisenstein series. And so for D4, you have a sum over like all vectors in the lattice such that the sum of
So typically putting more and more points make it, naively speaking, more and more convergent.
yes, sure.
Yeah.
Yeah. But so the problem is that, so for example, for D4, well, it's also convergent, but how to compute it? So, because when you have three vectors with sum zero, it's basically you choose any two vectors and the third vector is determinant. But when you have four vectors on the plane with sum zero, you don't know which three of them to choose, for example. Because when you have three of them, two of them must be in the same half plane. But when you have four, like many different positions, many cases, and so on. So and when you have five, it's even more complicated. So in many articles in this subject, people just start working with graphs. They don't even give the definition of the formula. They just say, well, we have such a graph, we have some cut and paste relations, and they compute something. But it's not clear what they compute unless unless you read this first article, which is fundamental.
And is there a direct geometric topological relation between these graphs and the topographs?
No, I have formulas only for CABC, because when you have CABC, you have a triples of vectors. And so here you have any triples, and for topograph, you have like super bases. But as I said, it's more or less the same. So if you compute everything for bases, like for any triples, more or less by standard methods. Maybe not vice versa, because, okay, let's go further. So now, why people study these things in like string theory and number theory? Because there are a lot of relations. So first of all, if we define Laplacian operator on these functions on the upper half plane, then this Eisenstein series, they are eigenvalues of this Laplacian. For example, how to see it the easiest way? You see, so here, this Laplacian on the like upper half plane, it's like that. And so, for example, if you look for the function y power s, then it's exactly, it will be like s times s minus 1 times y power s. Exactly because you multiply by y power 2. Okay? So for this kind of function, it's easy to see. But what happens with Eisenstein series? For Eisenstein series, you like consider a sum of the vectors. But then if you apply the SL to Z transformation, so you know that so for example, if you apply A, B, C, D to I, okay, and then you ask, okay, what is the imaginary part of it? It will be exactly, well, let's say here it's not y, but let's say x plus iy. Then the imaginary part will be y divided by c z plus d. Okay, so if this is z. So actually, if here y was just the imaginary part of z, and you had something like y power s, then for this expression, you have the same relation because the Laplacian is a set to the invariant. And so the same is true about all these functions. So since you have expressions like that in the denominator, like y divided by like nz plus m to s, and here s, you know how to compute Laplacian. It's just the same as you just compute the Laplacian for y power s, where z is x plus iy. Okay, and because of that, it's easy to compute Laplacians for all these functions. And so, for example, you can see that the Laplacian of C111 is 6 times E3. And then what Zagir proved, he proved that C111 it's E3 plus zeta of 3. Okay, now let's see. So what depends on tau? This depends on tau, and this depends on tau. Right, but this E3 of tau, what is that? That actually just sum over 1, and here you have this all this tau from the lattice, power 6, right? So this corresponds to the case when here all 3 vectors are collinear. Okay, so if you have 3 collinear vectors, so basically just the same as like 1 divided by tau power 6 times 1 divided by like sum of 1 divided by bd b plus d. Because like, for example, p alpha is like b tau, p beta is d tau, and p gamma is minus b plus d tau. And so this function, this sum you can compute. This sum is just Eisenstein series E3. So what it means? It means that if you remove from C111 collinear terms, so the terms when you have like collinear p alpha, p beta, p gamma, then it will be constant. It will be just zeta of 3. Well, and you see it. Because of that, when you compute the Laplacian, here you have just 6 E3. So first people computed, this is like in string theory, the Laplacian, because it's easy to compute. And then they said, well, if the Laplacian is 6 E3, that maybe if you just remove E3 from your function, maybe the rest will be the constant. And that's exactly what we had seen on the previous lectures. So when you take certain sum over topographs, it's a constant. It does not depend on topograph. Okay, let me mention more identities. So these identities are easy to prove. So you just compute it using the relations. You compute them. But for example, this. Okay, so here should be equality here. It was a question because maybe you can compute it, but it's not clear why it's true. So you just look for the first few terms in the expansion and you see that it's correct. And then you say as well, since they are modular functions, maybe you have the equality. Or this one. Okay, and then how people prove them. So the proofs are in this like article here, identities. So, well, as you see, so when you have such expressions, you have in denominators, you have certain kind of such sums. You have like complex number plus n, and you sum over all n, which is integer. And you can express it in a standard way. So this sum, think just this one. It's a very famous formula, maybe due to Euler. Then you change this to Q, and now you have this expression in Q. Then you expand all your function in Q. Then you look for the first few coefficients for Q1, Q square, Q cube. You observe that they are the same for these functions on the left and the right. Then you have estimate that these things, they grow at most polynomially at infinity. And since they're all modular, they have the first coefficients equal, they must be equal. Which is, so proofs are very not direct. So you just expand something. Maybe it's convergent. I think usually yes, but proofs are not very explicit. So I hope to reprove some of them using my telescopic methods. Maybe it will be like easier. Okay, now let's jump to the almost similar.
But what this is saying is that certain these modular forms and things like that can be seen as sections on some bundles or whatever.
Yeah.
Um,
Yes. So since some modular functions, you can also multiply by dz, and then you have modular forms on the torus.
that's right.
Yeah.
And so it's the fact that these spaces of sections or whatever are finite dimensional, or why just checking a few coefficients it's enough typically, or is not that the fact?
Well, at least it's claimed to be true. It's not like
Uh-huh.
they prove. They just say, well, like everybody knows that, and I don't know. So maybe it's obvious.
Mhm. Well, it sounds like this some space of Ship cohomology finite dimension. That's why they know this or something like that.
Well,
Uh,
they just compute everything. So they just look for the bases. They have huge programs in Mathematica or MATLAB, I don't know, and have
uh,
huge tables of dimensions and so on. So it's a lot of computations actually. And
uh,
I think some of them are proven, some of them are not proven, or maybe some of them are proven according to like physics standards. Like if you have certain formulas, you use them. Maybe if you don't care about convergence in the intermediate steps, maybe it's okay. I don't know. You see, it's just hundreds of articles. I don't see
uh,
why how to check it. But I believe it's true because no, like it's like modular functions and dimension is finite. Maybe how do you estimate the dimension? I don't know. They say okay, so here the dimension is 8, so it's enough to check 8 coefficients. Okay, I don't know. Okay, now let me tell the same, but in terms of Poincare series. But actually, that's the same thing. And this thing, they appeared in quadratic forms. So like last two talks about quadratic forms, there's like uh, Hurwitz class number formula. There are like several articles how they obtained, and they use the language of Poincare series. And they never cite this string theorists because maybe they don't know about the existence. So kind of like they have two branches of the same subject, and they don't know about each other. In one subject, there are like hundreds of string theorists, and in another part, you have like three mathematicians like writing three articles. Well, so here, what is the Poincare series? Again, so you have a group gamma SL to Z, or it may be some subgroup of SL to Z, and you have a tau from the upper half plane, and then you just you just apply gamma to tau, and you take a sum for certain function h. And clearly that's a SL to Z invariant because it's defined to be SL to Z invariant. Now, what function to h to choose? Well, so here you can put some parameters, for example, S1, S2, and 3. And to get these expressions, as we had before, you should put here this function h. Again, maybe it's kind of some standard thing, or maybe these mathematicians, they developed just because of Hurwitz summation formulas. But anyway, that's expression very similar to that we have seen before. Because, well, actually, I wanted to make some computation, but maybe I don't have time to do it. So if you put here tau equals this one, just AI plus B, CI plus D, then these things become just 1 divided by A square plus B square, I think C2, A minus C square plus B minus D square C3, and times C square plus D square power C1. So in this case, it will be just 1 divided by x square, y square, x minus y square. So actually, just again, the same expression. So here you just need to compute basically what is the imaginary part of gamma. of tau, and that's that's 1 divided by c squared plus d squared actually. And you also compute these things, and you just see this expression. So actually, that's just another form to write again the same expression above, because what happens above we take three vectors with sum 0, right? And here we take again three vectors, but we take 1, tau, and tau minus 1. Well, and some of them are also 0 if you put some signs. Tau plus 1 minus tau plus minus 1. And since anyway you plug here any tau, well, it's just the same function. So this h tau 1, 1, 1, that's basically the same as C1, 1, 1. Maybe up to a constant or just change of coordinate. Okay, and so what was the connection between topographs and Poincare series? That what we have seen the previous lecture, that if you have a quadratic form Q, ax squared plus bxy plus cy squared, you can consider the root of the equation az squared plus bz plus c equals 0. It has this root. And then if you plug this root into this Poincare series, you have some constant times this thing. And well, so here you have a, c, a plus b plus c. Okay, and that's h, right? And then you need to compute p. P is when you apply all the cell to z transformations and take a sum. So what it means, as you remember, applying a cell to z transformation to zq means passing to the root of the equivalent quadratic form. So it means that when you compute this p1, 1, 1, as I already discussed before, that it's the same as like it's a constant 3 pi over 2, because it's more or less the same as like C111 minus this E3, because I don't allow like collinear vectors. So here for tau, they are all not collinear. So it's a constant, but on the other point of view, it's just the sum over all a plus b plus c, when I take a sum over all possible quadratic forms equivalent to the given form Q. So that's how, that's the Hurwitz formula. So as you remember, so that's 100, so 95, 9005, that's the class number for the negative discriminant, it's certain constant, times this sum. Here I take all A, B, C, and that's exactly all the forms A, B, C with discriminant D, right? Because you remember, so if I consider all the forms with discriminant D, so each class of equivalence correspond to a topograph. And when so I just have this number of topographs. And when I take the sum over all these expressions over one topograph, it gives me a constant. So it means that the total sum is just proportional to h of d up to some constant. So that's how it's reformulated in this article of Sullivan last time, that if I have a topograph and I consider this product over all the vertices, that's just 4 pi up to a constant d. And then it means that you can consider other sums over topograph. For example, this corresponds to C221. So again, if you look here for the form for C221, so what was here? Yeah, you see, so again, here you have this E5, which correspond to the terms which are collinear plus a constant. So actually C221, so if you remove the collinear vectors, it's a constant. So this corresponds to the case that here P tau 221 is constant. And again, it gives you a formula for quadratic class number, like here. Well, any questions? So somehow I connected the string theory formulas to quadratic class number. They're just the same formulas, but under different disguise.
So
What
just
is
in general,
constants?
Sorry?
Misha first.
yeah. So you do everything with respect to S to Z.
Yeah.
Doesn't exist anything with S of 3Z? S of 3.
No.
So nothing.
Well,
Okay.
so for example, in string theory, they work with surfaces. So kind of the first expansion, they correspond to genus 0. Then you have genus 1. Okay, then maybe you have genus 2. So for genus 2, you should take this group of automorphisms of the surface of genus 2. This group.
So like nothing plus B.
Yeah. And then you have like similar formulas, maybe, or maybe not. Maybe it's too complicated. Then for topographs, again, there are no three-dimensional topographs. And also here, so here, if you have a quadratic form in two variables, then there is a very nice bijection between the action of SL to Z, and it acts on the upper half plane, and so on. If you have form in three variables, then you cannot associate a root to it, right? You can associate maybe a curve. And then you have curves and you have action of SL3Z on these curves, but what to do with them? So I don't know how to do anything for SL3Z. So in any of directions.
No, in the in the loop formalism, in the string theory formalism,
Mhm.
you ignore the mild dependence. You get a zeta function value constant.
Yeah.
While on the topograph discussion, you get multiples of pi. So what's the relation between these constants?
Oh, this I can tell you, because as we will see later, so this telescopic summation gives you angle. And since the total angle is 2 pi, well, you have 2
Yeah.
pi. And that's how you get kind of the C111 thing. And all the others, they somehow, like there is a recurrence relation. So if kind of the first term is like depend on pi, then all the others also depend on pi.
But the appearance of the zeta function in the other thing comes because it's you are adding over more things, or
Well, for example, let me explain you z of 3 here, right? So here you have z of 3. Z of 3 comes from this term, well, here. Because you can multiply b, d, and b plus d by any number. And so if you say that they are coprime, for example, it means that you have a factor of z of 3.
okay.
So actually, this
Okay.
z of 3 or z of 5, they're here for stupid reason. So because, for example, you have just product of 5 numbers, and if they have GCD n, you just divide by n. And that's why you have z of 5. So, okay, now how to get more relations that also I discovered by myself, rediscovered. That when you have just three variables, well, this C, A, B, C, you can also put the index here, K, and put here the determinant of the matrix of n and m power to k. So you don't only care about three vectors with some 0, you also grade them by the area of this parallelogram they span. And then first of all, you have a relation for Laplacian, just purely formal. You just differentiate it and you see it immediately. And well, so when you differentiate here, you get A. When you differentiate here, you get B. Well, and so on. And then all the other terms, they cancel. Well, and also you have a relation of degree 4 for any vectors that also I discovered by myself through enormous computation of cases and so on. The relation is like this. So if you have 3 vectors with some 0, then if you take the squares of their norms, or just, the length power 4, and you subtract the sum of squares, it can be computed using the area. And so here this tau 2 is just the same as y. Okay, so this tau is tau 1 plus I tau 2. So this tau is just the area of fundamental parallelogram of the lattice. And using this relation, you can also plug it into this formalism, and then you just have all the relations. So maybe there are other relations, but then they're like conjectural or very difficult to prove. But using these two kind of relations, you can compute just almost everything, I think. And anyway, since they're quite big relations, you need to do it on computer. That's what these people do. So you have a lot of relations, okay? And basically, you need to compute just C111, and then everything else is done by machinery. Okay, now let me tell you about my results about how the telescope thinks and why it works. And so in the remaining 10 minutes. Okay, as you remember, we have a topograph. So we have like this 3-variant tree in the plane, and then we have labels on the regions, and we have labels on the edges, and then labels on regions satisfy this rule. So R plus U is 2 times S plus T. So this R, S plus T and U, they form a arithmetic progression. And we write the difference here on the edge. So this G is just S plus T minus R, or it's U minus S plus T. Okay, just the same. And then if we know the labels on edges, we can recover the labels on regions. And so this thing corresponds to a binary quadratic form, because you can write here basis vectors, E1 plus E2, and here like 2E1 plus E2. And then you can just evaluate your quadratic form on these vectors. That's how you get labels on regions. They satisfy this rule, and well, so you have a topograph associated to every binary quadratic form. And then the discriminant of the quadratic form can be computed using this expression. So it's the same for all the vertices. Now, how to get the telescoping identities? Very simple. So let's just look at the following sum. So here I have G divided by ST minus H divided by US minus I divided by UT. Okay, so here I orient edges H and I outside of this vertex, but if I orient them all inside, so it will be just the sum. Right, so here I have S, T, U, here I have G, here I have I, here I have H. So just this expression. Then I remember what is this U, just H, I plus H divided by 2. And then I just see that on top I have 2D. So it means that if I telescope this expression over the whole topograph, I have just 2D divided by the sum of 1 of STU. Right, so what was the telescoping? So just look at the picture here again. So here I have G divided by ST, then minus H divided by US, and I divided by UT. Then I have the same sum for this vertex. So I add this thing and subtract this and this. So for the graph, it looks like that. So you have a tree, nice tree. So you have a root, and so here the sum that corresponds to root it remains, and then all the internal terms they cancel, and then I have a crown. Why it's not strange? Well, so then I have a crown, and so I have a sum over all the edges corresponding to the crown of the same kind of terms. So I have here an edge, I don't know, G, I have S and U. So here the term corresponding to this edge is just S, well, G divided by SU. So, or you may think that I just, when I take the sum of 1 over STU over all the vertices inside here, I have just the remaining terms of the bound. And actually, what is fine, funny that you can do the same when you revert the edges and regions. So here I have a label on edge divided by labels on the regions. But I can do symmetric thing. I can take the labels on the regions divided by the labels on the edges. Because finally the identity will be exactly the same. Here I have this kind of product. So in a similar way, I can sum 1 divided by EFG over all vertices with labels EFG. Okay, so here we had a formula for sum over the labels on the regions. On also previous time, we had a sum for the, it was, oh, okay, I removed that. So when you have a topograph of, okay, so let me summarize the result here. So when we have a branch of a topograph starting from some moment, and then we take a sum over one of RST labels on regions, we can recover the class number formula for D less than 0. And we recover this C111 and also the CABC just by recurrence relations. And this corresponds to the area of the ellipse, because the quadratic form with negative discriminant defines you an ellipse. So that's how we proved the formula for the circle. When we telescope 1 divided by EFG labels on edges, as we seen last time, the previous time, that gives a class number formula for positive discriminant. And then you can ask, okay, so what happens if I telescope 1 EFG for negative discriminant? Actually, it will be just the area outside. So when you compute the sum of the 1 divided by RST, it will be this area for the circle. And when you compute the sum of the outside, so here I have this kind of triangles. And when instead of looking triangles inside, I draw tangents at these points and look for the areas between tangents, exactly the same points. Then it's a direct computation. This area here, it will be the sum of 1 over EFG. So the sum over the edges labels. So this way, maybe you can understand what is this, why we compute this class number formula for D bigger than 0 of edges. Because if you have a ellipse, you count triangles inside. But if your discriminant is positive, so you have kind of hyperbola. And it's not clear what to compute inside, but maybe it's easier to compute something outside. So this thing corresponds to the class number formula here. And you need to telescope over the edges. And finally, to answer the question of Ernesto, why we have pi, just a computational question. Okay, so let's say we have a quadratic form, and we have this topograph, and we want to telescope, this sum or this sum. So how to compute it? As you remember, we have summons corresponding to the root, and we have summons corresponding to the crown of this tree. And as we have seen for the case of the simplest case that we had, in the very beginning of the lectures. So here, that's how we started. So we said that we just telescope this kind of function. In this function, just measure you the angle in your sector. Actually, the same happens for every quadratic form. So I just discovered this formula today, finally. So what happens for the area for the general quadratic form? Again, so let's just try to reason heuristically. So we have terms like g divided by st. For the case of the standard form, just x squared plus y squared, this corresponds to the scalar product divided by this thing, which is just proportional, which is equal to sine of 2 alpha. So if you have two vectors which span a parallelogram of area 1, you take their product, you divide by the product of the lengths, then it's just the sine of 2 alpha here. And then when you take a sum or all of many small parallelograms like that, they just partition the angle. So the sum of the angles is like pi over 2 or pi or something. In general, you can do the same. So you just say that for a general quadratic form, if this thing is small, then it's proportional to its arc sign, plus some small order terms, which will, well, anyway disappear when you take a summation. And then the correct formula is as follows. So what is interesting? So for any topograph, so if you just look for this expression, you just look g divided by st, and then you multiply by square root of minus discriminant by 4. So if your discriminant is positive, this becomes complex number, but it's fine. Why not? Then you have the following identity. So it just follows from the properties of a topograph that this kind of arcsine is equal to arcsine of the next terms. So this GST, HSU, and ITU, that exactly terms that we had here on this picture. Here, G is 2, H here, and this Y. So just those terms at the one vertex. And they're just actually angles. So you just need to multiply by this expression, and then you have this condition for arcsines. And then instead of summing this expression over the crown, you say, well, instead of these things, let's sum the arcsine, but the arcsine satisfies this nice expression. So it's just the same as the measure of arcsine of the two vectors at the root of E1, E2. So the whole telescopic formula gives you the following. So the sum of 1 over RST over all this like branch of the tree is just this value of this function at the root minus arcsine of this value at the root. And then you also have some constants here, here, and so on. And so if you plug all that for the initial formula for the sum of these like squares, so here the form is like x squared plus y squared. The discriminant is minus 4. So here you have minus 8. So here you have 0. Here you have 4 over 2 times pi, because we have twice the angle here. So here the angle is pi over 2, but we have twice the angle. So it will be pi multiplied by this constant, which is just the square root of minus d divided by 4, like 2 divided by 4. When you compute it, well, you have the correct value of pi over 4. But what is good, I think, is that, so all these guys, like in string theory and Poincare series, basically they consider this kind of form. Or if you choose another basis, okay, so kind of instead of this form, you consider the form like ax squared plus by squared. But what I have, it's more simple and it works for any form, for negative discriminant also. So actually we don't care about the thing. And it can be computed explicitly. Well, that's all I wanted to tell you. That's all.
Thank you. Thank you very much. Yeah, quite outstanding. So thanks a lot. So any questions? Do you have any question?
Thank you very much. Uh, I'm not expecting anything to read, but in quantum field theory, specifically in particle physics, when we deal with Feynman diagrams, specifically when we face with loops, we have kind of divergent terms in the theory, and they are really useful for particle physicists. Of course, I'm not one. Did you see, or can you comment on these kind of divergences in your theory? Did you see these kind of divergent terms? Specifically, they should be related to tau. I think so.
Well, so
for
here,
a specific.
so indeed, so you may have divergence here, for example, as follows. So when you plug here, let's say, mm, yeah, for example, here, you may consider not only like C, A, B, C, you may consider C minus 1, 1, 2, something like that.
Mhm.
So from this definition, maybe it's not okay because it means that you have minus one edge. So what does it mean? But it's good from the sense of these relations. So instead, because there are relations for any like A, B, C, and K. And so indeed, you may consider the divergent series. So, and then you have relation between divergent series and convergent series. And maybe it's interesting because maybe it shows some cancellation. So maybe something like C minus 1 minus 1, 4. If you subtract something, minus 1 minus 3, 5. Maybe if you just cancel all the wrong terms, then you have something convergent.
Mhm.
Also, there are
Okay.
certain series which are convergent in some setting and divergent in other setting. For example, so here, uh, for example, here, you may consider the sum over all like expressions, but you take vectors only from one quadrant and you have a restriction for the determinant. You say it's not zero, it's not big, just one. Then it may happen that certain series converges here. But if you take a series over all, like vectors PA plus PB plus PC equals zero, then it diverges. But still you have the same relations, and maybe if you add some small parameter, there is a way to get some identities and then to prove them. Um, but I don't know what is the influence of these computations for this type 2 superstring amplitude lower energy expansion. For me, it seems it's just nice number theoretic formulas. And
Actually, I have no idea on those things, but yes, me, I don't know.
because no, they
Well,
just
essentially,
have some expansion of some integral. Okay, you write integral, it diverges, you have expansion, and then you study coefficients, and you study them very thoroughly. You just want to know everything about the coefficients. But what is the use for understanding the initial function? I don't know.
really. Yeah, thank you for the comments.
Thank you.
Uh, More questions from the Zoom, perhaps? Okay. If not, thanks a lot, Nikita. It was really nice.
Thank you very much.
Bye-bye.
Thank you.